Recording in progress. Hi, everybody. I'm Devin Smith. I have a pop-up above my slides. I have recently been appointed CTO at QuiX Quantum, but before that, I had to click on the slides. Yeah, right after I clicked on Zoom. Was an academic for a long time. So only in late 2022 did I defect from the world of academia and become an industrial person. And that was mostly because after a PhD, where I spent a bunch of time standing in a dark room playing with a single photon source, it became clear to me that we need integrated photonics if we ever wanted to make a quantum computer out of photons. And so I went off to go learn how to do that, and spent a couple of years in Japan at NTT Labs, and then far too long in Brexit Britain at Southampton, working in silica. And it turns out that the kinds of research that I'm interested in are also the kinds of research that academics, or at least people that give money to academics, are less interested in, which is to say that technical advances necessary to really make things possible. So it's not necessarily the case that actually making a good switch for quantum light or a good source of single photons is a fundable piece of research. There's this sort of like tendency for academia to chase the new, sexy, cool way to do something, whereas when it's time to just put hard yards in and turn something from an idea into a commercializable product, often there's a lack of funding, and unfortunately, this money runs out before the commercializable money turns up. Quantum technology is currently in a state where there's a bunch of venture capital piling into something that, frankly, they're not going to make any money off of for a long time, and that's good for us. But lots of technologies in lots of countries fall into some sort of valley of death, where a good idea can't get funded to become a real product. And how far up the tree that is depends on the country, but many countries have this problem. And so that's why I'm now an industry person. This industry will pay me to do work on the things that I think are important. Things that are important are actually accomplishing. This is a slide from Yelmer, now our chief scientist, about why quantum technology is fun. In his opinion, the theorists are over here, and what we know about making the experiments is on the other side of this bridge, and then we're working our way towards each other. So our understanding of how to make stuff is emerging from the sort of engineering landscape, and we're attempting to bridge the gap to universal quantum computing with near-term stuff. This bridge might fall down on the NISC step, but maybe we can build a bigger and better one in the future. And of course, our goal is as always to bring these closer together. I think Yelmer fails at art, because for me, this looks like an optical illusion where the two sides of the bridge now look like they don't meet up, but yet another problem with theory. So this talk will be
It's more fun on the left side than on the right side.
Well, I'm an engineer, and so for me, the fun is making sure that the bridge doesn't fall down. I swore an oath about that. So this talk will be in two parts, in fact. There will be an initial section, my labels are gone, about sort of the near term, what QuiX has, what we might want to do with it, what we need you guys to tell us about, what we could do with it, because that's looking pretty shaky. And then a second part on how we're going to build a universal quantum computer, why we think photons are a reasonable thing to make the universal quantum computer out of, and again, what it is that quantum software or QuSoft could help with us, could help with. So first, all of this will be so-called linear optics. So you can show that if you can do nonlinear optics, where some property that scales faster than the photon number matters, you can win really fast in making a quantum computer out of light, but we don't know how to do that. And in fact, there's good reasons to believe we can't do that. It turns out that nonlinear optics as a field mostly studies things that are much brighter than this laser pointer. And this laser pointer is already 1 trillion times brighter than this photon. So we're just going to study things that that depend only on the photon number. And this implies that there's no photon-photon interactions. But there are quantum effects left. There is the very, very famous, yeah.
Sorry, do you mean that nonlinear effects only take place at super high intensities and they're not important?
Yes, so if we could, they would be important if we could have them, but we can't. So if you can make, if you could make some interaction that happen faster on two photons than happen on two individual photons, then your entangling is very easy. But as it happens, we don't know any way to do that. And so given that this is all we have access to, can we still get some more interesting? Sorry, and I didn't say it, and I assumed given there's a whiteboard and a bunch of theorists in the room, please ask questions. And I might have to defer you to the end of the talk or to a later slide, but I'd rather that than have people go, well, what's the stupid experiment I was talking about? So there's one very famous thing going on. That's the so-called Hollow-Mandel interference property. So if you take a beam splitter and you shine two photons into it, it is always the case that they come out together. It turns out that this is quite independent of how you make this beam splitter. So there might be an additional phase term between this guy and this guy, depending on how the beam splitter is constructed. Basically, any way you can think of where half the photons go through a window and half the photons bounce off a window, you get this effect. As long as these two photons are indistinguishable. So, of course, we have to make indistinguishable photons. That turns out to be a major experimental task. But for the purposes of doing theory, you can just assume that we've done that part and carry on. And of course, this effect is generic for all bosons, but all the other bosons are quite hard to work with. LIGO is a huge machine designed for detecting like tandem gravitons. We're not using those. There are some artificial bosons where this also comes out, but photons are by far the most successful version. And this process generalizes naturally to n photons. You can think of this as n pairwise interactions where it becomes sort of combinatorially complicated, but the various paths interfere in factorial ways. And there's no way to simplify this calculation below exponential star unless p equals np, or the polynomial hierarchy collapses, or some other computer science condition. But for the purposes of my physics talk, I'm going to say there's no way to do it. Yeah.
Sort of on the slide back when you have this whole Mandel effect. But I mean, I guess this generates entanglements.
Yes.
Right? Because in superposition, they either go both left or
yes,
and both right.
So yes, this is a source of entanglement. Unfortunately, it's kind of an awkward source of entanglement because this so-called noon state of 2, 0, and 0, 2 is very useful for various sensing applications, but is quite challenging to use for computational applications. And if you then put two photons in each side, the state you get out is not 4, 0, 0, 4, but the mixture of all the even photon numbers. The so-called, so this is a 2-photon noon state, and the one that I just mentioned has the delightfully named poop state because it is no good. All right. Yes. But our unitary here, and this unitary is not acting on the cubic basis. This is unitary acting on a basis of creation operators. So you can think of this as a super operator acting on a vector of operators. I'll get to that in a second. But don't just, I guess, keep in the back of your mind, this is not a unitary on the cubic basis. Our device does all of this calculation for free. And so you can sample this output exponentially better using linear optics than we can if we try to sample this output in a classical machine. Since this is an example of a problem that sits in a complexity class that Scott had to make up in order to show a gap. But it's so-called sampling sharp P, which you can tell is not a real complexity class because it's got a really long name. But Scott and who's an old, he in fact taught me when I was a master's student. And one of his students, Alex, wrote this 100-page paper. Oh, this is the short version. There's a 100-page version of this paper showing that this problem shows a gap between an exponential gap between classical and quantum. Now, problem. It's not actually any good, useful for anything interesting. So, of course, it shows a quantum advantage, but
it's conditional on a couple of conjectures.
Yes, but those conjectures seem pretty strong.
They're not all as
believable. This is again a slide from Yelmer, and it's slightly stronger than I would like to write. But the barrier of simulability, at least at present, is somewhere around 50 photons. That sort of ballpark. And it's in some sense a computer, though of course it's not universal. And so it's only applicable to certain very limited set of problems. Now that limited set of problems might be an interesting set, but if you look through the literature on all the sort of NISQI applications that people have come up with for one of these devices, something like 80% of the papers are either just wrong or true. So in many cases, the quantum character of the output is not necessary for the result that they show. And that makes the device classically simulable, and that means that the quantum classical gap. So an application for such a device that's actually useful to someone that is trying to accomplish a task that they care about, as opposed to just a task that shows that quantum computers are great. As far as we can tell, does not exist. In fact, this Nature Photonics paper, that result is not actually useful. Again, it does not show an actual advantage for the quantum algorithm. It just shows that linear optics with a laser beam, a linear optics laser beam would come up with the same answer as with single photons. There's no necessity for the entanglement. So if you want a really sexy patent, or just to make all of the photonics people, the experimental photonics people in the world very happy, coming up with a good and useful application here is something that we are very interested in. And of course, machine learning is on the list. Machine learning is on the list partly because there are sort of convincing arguments, partly because machine learning is all a giant ball of hard to prove conjectures about runtimes and so on. So maybe there's something there, but that might be a place where we actually have to sit down and start actually making machine learning models on a practical device in order to show something. I don't know. I would love to hear about it.
I guess what you want to say is that they are on your wish list.
Yes, very much.
You mentioned that, so I don't entirely understand why you have a single photon source, because especially you said also in linear optics you have no photon-photon interaction. So something distributions.
Sorry.
That's the laser.
Right. So if these inputs are up to 1 photon each, right, then the calculation of this output distribution is classically hard. However, if these inputs are laser beams or other otherwise distinguishable inputs, then this output distribution is not classically hard.
Yeah, I guess because of this effect.
Yeah. So there's no
reason for
this combinatorial blow up doesn't happen. Here is a diagram of the demonstration done in China by Chaiyun Liu and some other people, many other people, demonstrating this protocol. This is a diagram that already makes me a little bit alarmed. And then here's what it looks like. And the assertion from Chaiyun is that this only took a month to set up. And I don't believe it. And so I put up my hand at a conference and I said, really? He said, yeah, it took about 4 PhD students working for a month. And then you go talk to the PhD students, they're like, yeah, working in our lab is great. Sometimes we get to go home early on Sundays if everything is going well. So, you know, who knows how many man-months that is of time if you don't abuse your students. There's a whole bunch of inputs, a bunch of numbers. The important thing is, you know, they've reached a huge state space. It's the largest coherent quantum system. But, and I've skipped over a couple of slides of back and forth. This paper by Google has the best simulator for this sort of process, and it that caused actually the Chinese to go back and make their experiment bigger and show that yes, even against the better algorithm, we can still get somewhere. However, this is not a device that can calculate a general instance. This thing in the middle has become even more bored over the years, is a bunch of bits of glass glued together. And this thing simulates or has exactly one setting. So if you'd like to put a particular input into this device, too bad, go and make a new one of these. That sucks. So this is where this is the QuiX pitch. We can make one. So our devices that we have available today, which again may or may not be useful depending on whether we come up with an application for them, in a computational sense, researchers are buying them to replace their labs, are built on a chip. The inputs and the outputs are on either sides here. And this is up to 20 modes. It's not 144 modes, but we're working on it. And we're doing all right. So QuiX was originally opened in Enschede. We've opened an office in Ulm because we managed to sell the Deutsch. One of these years I will stop stumbling across that. The German Aerospace Center, a quantum computer, a real honest to God quantum computer. We'll get to that in a minute. We've also obviously sold some of these processors over the years. So there's an office in Ulm to deal with the Germans, an office in Amsterdam to deal with you guys. So there's a container just around the corner with our name on it. And then Bard will be here on a regular basis. Of course, we made the news for selling things. This is our local paper. And here's Yummer saying something that I hope is very clever, but I can't read it. So so here's what the devices look like on the table. This fits in a 19-inch rack. So it'll go in your server room with everything else. And of course, what you want is for this thing to not screw up your quantum line. I'm going to skip over this stuff relatively quickly. But it's the largest device of this type that anybody's made in the literature. It consists of nothing more, nothing less than a literal array of waveguides with phase shifters, with tunable beam splitters and tunable phases at each unit cell. Because the size of a unitary matrix goes like the square of the number of the side length, these devices get quadratically bigger as we go, which might be one indication that this is not the way to build a universal computer. We know that. We make out of silicon nitride, which happens to be a material that's got.
They get quadratically bigger. What do you mean?
So
because it's like
it's a square, yeah.
Okay.
So if you have n inputs and outputs, the matrix that describes that has n times n minus 1 as free parameters.
You could also look at it, this matrix has n squared parameters roughly.
Exactly. So the number of free parameters in the matrix is exactly the number of tunable elements in our device. And the reason for that is that otherwise calculating what the element value should be is hard. Or rather, it's not hard in a technical sense, but it's difficult. So there's an exact algorithm for just an analytic one, as long as the number of parameter count is exactly.
And another thing still is in my head, because you said if you shine on just a laser beam in it, then it's easy to predict how it goes.
Yes.
But I guess if you were to care about the intensity, then it becomes hard again.
No. And in fact, I will show some characterization data in a moment. All of our characterization data is taken with a laser. The the step that sort of raises the difficulty is that the unitary that describes this transformation is again acting on the vector of creation operators at the inputs and the outputs. And so if you then put in a particular input state that generates a combinatorially larger matrix that describes the evolution of those photons. You're looking at me suspiciously, so we'll talk about this Saturday.
Yeah, what? Yeah, let's maybe do it after the talk.
And here's us just claiming that we're great. We make a bigger thing with lower loss than anybody else. In practice, the major difficulty is that setting 380 elements on a single chip accurately is difficult because they talk to each other. And so we've got a fairly long research project built into making sure that when you set, this exact value, it sets only that and only that value. So we're much better at setting permutation matrices than a random unitary. Here is an example pair, and I think if you look very carefully, you can see the difference. But he's chosen a different random set than, there's a different random pair than I usually use, so I don't know where the difference is, but those are roughly 2% different. Now, I mentioned that we're measuring these using a laser because you get statistics much faster. And so we've lost the phase data here. But we've done some alternative measurements that show that the infidelity, so 1 minus this fidelity, is approximately double if you include the phase measure. And of course, one of the lovely things about photons is that it's very, very hard to destroy coherence. You can lose your photons, in which case they're not coherent anymore. But as long as both the photons turn up at the output, they continue to be entangled, basically no matter what you do. And so here's a measure of the quantum coherence. This is limited by our source visibility. And unfortunately, our off-chip benchmark for the source visibility is lower than our on-chip measurement. And so I don't actually have a good. And then another thing that may be of interest to the group here is that we're putting this online starting in all the APIs going to be delivered at the end of Q1, so early Q2, we're hoping to have early access available. So if you want to play with a thing like one of these things, see if you have some QML problem or some server search problem that you can run on our system, it'll be available over the cloud, and for collaborators and so on, there'll be and certainly alpha and beta users, there will be it'll be mostly free. So all right, that's the end of my talking about today. How am I doing on time? I'm just going to shift gears. Any other questions on this?
As I understood it, it's always difficult if you have photons from different sources to do this Hanger-Mandel interference.
Yes.
How do you guys have one photon source and you split it, or do you have multiple photon sources?
So those measurements are made with 2 photons from the same source. Our setup in the lab that we're putting online is actually using a single quantum dot, which emits a stream of photons every 80 megahertz. And then you just take this batch and you delay this one to here and so on, such that you get 6 across instead of 6 deep. Because it does turn out that making high brightness identical single photon sources is probably the single biggest problem in the field, which is very frustrating. It's a very easy to describe problem, and yet is a very hard problem to solve. And so there's, in fact, several different research lines going on at QuiX and elsewhere, trying to solve that problem. And so I'll mention some of that coming up.
So how do you delay them? By running them through a little.
So there's a free space switch, basically just steers them into different fibers. Those fibers are all chosen to be the right length so that they all come out at the same time. One of the delays we're talking about here are small enough that the dispersion and the loss in the fiber is almost irrelevant. the longest delay line is about 900 meters, which in fiber optic terms is not much.
Oh, but then you do have some photon loss.
We do, yes.
And also the switch probably.
But yeah, the switch is a much bigger problem than the fiber is. But conditioned on the photons arriving. So in post-selection, the interference is not degraded.
But what's your loss?
So I don't know, to be honest. So our total success probability from here to there is about 18%, which is way below spec on the device we bought. So
You synchronize them by having some of them traverse a longer path.
Yeah.
That's saying something really stupid now, but I thought there's also materials that in which the speed of light is lower.
yes, there are.
That's not useful.
So no, it turns out that the best place to store a photon to avoid it getting damaged is in free space, in just the air. And the second best place is in optical fiber. Because slow light media tend to be, the loss per unit time is much higher. And so the really dumb answer of a spool of telecommunications fiber is by far the best medium for quantum memory in light. So you will see lots and lots of scientific talks about making quantum memories for light out of atomic vapors of various kinds and so on and so forth. You actually calculate the performance of that versus just a loop of optical fiber with a switch. This is much better. This is not publishable, unfortunately, but in practice, it's the performance is substantially better for just the dumbest possible thing than it is for almost all of the very clever quantum memory research. And in fact, the single best light source for making batches of photons at the same time is in Illinois in the lab of Paul Quid, and it's on table free space loops running around a racetrack on his table for up to 400 meters, just back and forth on his optical bench, and his loss is much lower than even the best fiber version.
Free space loops are just a bunch of mirrors.
Yeah.
That's not you're using fiber optic.
We're using fiber optic.
Why aren't you using free space loops?
Because the maintenance cost is about an hour a day on Paul's system. So they turn up in the morning and even with a quite well temperature stabilized lab, have to realign the system. And the nice thing about fiber is mostly nothing happens. Sorry, I had to take that one. So you've all seen, well, one, this sort of picture many times, and also probably this sort of picture many times. So this is a superconducting quantum computer sitting in the bottom of a fridge with control lines like you wouldn't believe running down to control a bunch of tiny little loops of superconductor. And the way that people think about it is you have some qubits, do some gates for a while, and then over here you're going to do some measurement. I don't know what happened to this core S. This is hard, right? And lots of work is going into making sure that your qubits are coherent enough to make it below the error threshold, into error correcting codes, into topologies for various, what topologies can you actually fit in a fridge? How can you make this modular? It's a big problem is if you start calculating how big a chip needs to be for any given useful problem size, that the answer is large enough to be a problem. Large enough you need to make a modular system. That's true in photonics, it's true in superconductors, it's true everywhere. Approximately everywhere. And one of the advantages photonics has is that if you can already put light in a fiber, you can choose a fiber and connect two different modules together. Making this thing modular is a problem that a whole company got founded to solve, QuiX in Delft. And it seems real hard. But doing gates, because of the aforementioned problem that photons don't interact, actually making gates in a photonic system is very hard. And so what we want to do is instead use what's called measurement-based quantum, which again is a multi-step process where first we create this large entangled network of qubits. So every circle here in this graph is a single photon or a quantum state of light encoding a qubit. And every edge on this graph is one maximally entangling gate. Choose your favorite one. In practice, you don't actually use entangling gates, but for sort of understanding purposes, that's sufficient. And then using only single qubit gates and measurements, it turns out you can then turn this into a processor that both you input data using measurements, you input your calculation doing measurements, then you redo your readout, you're doing measurements. And measurements we're good at. Right? So if only we could make this thing, we're good to go. Now, unsurprisingly, this whole thing is teleportation over and over and over again. And so you need to do what's called feed forward to select the forward going measurements. So at each step, you take a bunch of measurements, and then you sort of teleport the results onto the next layer using by a choice of the measurement basis, the next layer of the computation. So that's the very beginning of measurement-based quantum computation. Now, the two questions arise. One is, how does this paradigm relate to the previous one, which I'll get to. And the second one is, how do you actually make this thing? Given a bunch of photons, how do you make such a state? One term of art that I would use is a cluster state is a graph state that is formed of a regular lattice. And then when people say graph state, they tend to mean non-lattice cluster states or non-cluster graph states. Now, why do we want to use measurement-based quantum computing? Well, one, we can't make gates, but the dominant error in photonics is photon loss. And photon loss is, it turns out, a really good error because it's an erasure of your qubit. It takes you out of the code space. It's easily detected and it's easily corrected. There's almost no other decoherence. So up to details, and those details are important. There's only one error channel, and it's a really good error channel. So the error threshold is in the tens of percents, be as high as 50%, depending on exactly how you put things together, as opposed to sort of ones and twos of percents in other systems. Surprise face.
50%.
50%.
Errors?
Yeah.
Per what?
Well, so we can only eat every photon once.
Okay.
Right.
So you have this whole bunch of photons, like the width of the circuit times the depth of the circuit.
And if we lose half of them, well, just slightly less than half, we might be good to go.
How does it scale? Because if you want to have many modes, and then you need more and more entanglement, so there should be, for a given like detection efficiency and also there should be like a threshold
Yes.
for what big system you can go, right?
Yes. So no. So if you have it's like other errors where once you're below threshold, there is a sort of divergence. I'm not used to running the truck anymore. So as you approach the some error threshold, the number of physical qubits you need for one logical qubit diverges, right? And that's true for every system. Exactly this divergence rate is something that I don't have off the top of my head, and in fact, I would like to know more about. But if you're below the error threshold, then in general, your state remains connected, even up to arbitrary sizes.
We remove this threshold for this scheme.
It's in a few slides, and it basically comes down to percolation theory on the graph.
These error rates of like 50% can be tolerated because they're erasure errors. You know where they appear, right?
Yeah.
Otherwise.
Yes, otherwise you're doing it, right? But the fact that it both is easily detected, it erases itself, and it doesn't then fuck everything else up again, means that loss is by far the best kind of error. That does mean that we have to be very careful not to accidentally put two photons in any one of these modes, because then that one photon can rattle into somewhere we lost a photon and turn up as a logical error. But So that's a problem on our end, in turn. And then this picture of there's some spatial extent with some number of modes in it, which defines the size of our calculation, and some time dimension that defines the sort of qubit length of the calculation, or the gate length of the calculation, is pretty accurate, right? We in principle can use time multiplexing, reuse the same components even more times, but in photonic quantum computing land, everything is qubits, right? So it's not, two qubit quantum volume is not gates times qubits, it's just qubits times more qubits. And in principle, you can sort of rearrange those qubits into a shape that is useful for the size and length of calculation you're trying to do. And then the other really important fact is we don't need to make this all at once. We only need a small portion of it to exist at any given time, because the information sort of flows through it as we make measurements on one side. It hasn't actually gotten to over here yet, right? So it sort of lives at the boundary of where the measurements are happening. And so as long as we keep sort of 1 to 2 layers of the cluster state alive at all times, our calculation can proceed. And so in classic cartoon fashion, as long as we can sort of put the railroads down as we go and pick it up from the other side, we are good to go. And so the total lifetime of any given photon in here is like 2 clock cycles, so 24 nanoseconds. Not, from here to there. Creating small cluster states from single photons turns out to be hard. There's well-known techniques for them, but they require a bunch of multiplexing. That's fine. If you are slightly more clever, you can generate small entangled cluster states directly using spin photon entanglement, which is fine. The next important step is that we aren't going to perform logical gates to glue these small cluster states together. We're going to fuse them in a way that is much more reliable than the sort of, let's just do a controlled Z gate sort of conceptual idea that we use to think about what this edge does. And the last thing we do is, out of the lattice that we formed, we carve our gates. So this is a diagram from the paper that showed the equivalence of measurement-based quantum computing with gate-based quantum computers. The red area on the right is a CNOT gate. And in principle, it can be done in one time step. You just go chonka and measure all those guys. And this one is a single qubit rotation. This is kind of inefficient in that if we've made a square lattice, we've just deleted huge swaths of it in order to sort of trace out these wires. But it's constant overhead. And so for computer science lands, that's good enough. I would love to see better versions of that. And we're working on this in the lab. So we're working with Candela and others to make cluster states. This entangling fusion operation is not literally the same chip we have today, but it's closely related. All the things we know about are useful. The one big addition is you need to have a delay line feedback loop recurrence in order for the time multiplexing to work. And the detectors are, in some sense, done. Good single photon detectors are in the world, ready to go. Please ask your question remotely, and we'll see if it happens.
Hi, on Zoom.
Yep. Hello, Zoom.
Hi, hi. I'm John. I was wondering, because here you have like a square cluster state, right? Like, is this something that's like very, you really need this shape for your hardware, or could you also do like hexagonal or some like much weirder shape?
We can do any state, any shape you like if you have a good reason for it. It turns out that something that is simply repeating in the time dimension is much easier to make, because we then don't have to adapt the configuration in the time dimension. But even that is in principle adaptable. So if there's a good reason for it, any convenient shape, or if the shape is better, I can put the hardware work in to make it
Okay, and when you say repeating in time dimension, you mean like strictly repeating, or more like cyclical would also be fine?
Cyclic would also be fine.
Hmm.
So the canonical lattice that gets used for thinking about this gate to measurement based lattice is this one here, which you can see is cyclic. And actually that one's not cyclic. Somebody's made a transcription error here. But the general thought that the way that people think about it, at least naively, is that each sort of line in time is one logical qubit sort of evolving. And so if the width of the cut at any given time step varies by a lot, either you have to use that extra width to do some logical operation, or you're going to sort of squeeze out information when you get narrower again.
Okay, and obviously with the graph state, you're working with like CZ interactions, which I assume are quite nice to do on the photonic level. Have you ever considered like hypergraph states where you have like more photons interact? Is that something that's physically possible?
So you can. People have looked into using hyperentanglement, or which say encoding multiple qubits in the same photon, which if your photons are very expensive is quite appealing, but the understanding of the community is that once you are good enough at making photons, using hyperentanglement is no longer helpful. And this is in some sense as much entanglement as you can get between two qubits without bad things happening.
Okay, thanks.
Maybe if I can ask, if I understand correctly, that this graph determines between what qubits you can do a CNOT gate. So if you make like a flat grid, if you want to have the first and the last qubit interact, that would be nasty because you need to have all kinds of swaps.
Yes.
I could almost see like a computer scientist cooking up a graph that has like, I don't know, still a low degree, but still pretty much connectivity to everything.
Yes. So it is. So let me wave around my hands for a second. The sort of naive thing that people think about if you're thinking about multidimensional lattice states is that you have one dimension of storage and then two spatial dimensions of error correction, right, for your X errors and your Z errors. And it's likely you want those X and Z directions to be toric, literally, edge mapped, but maybe not. And exactly how big they are to be determined. But then the sort of logical direction, almost certainly you're better off with something that is partially scale free rather than a single one-dimensional line for exactly the reason you're talking about. It's sort of moving stuff around becomes much easier. And in fact, on my, no, not quite next. Coming up is my list of open questions, and you've gotten to one of them, which is what topology is optimal, what geometry is optimal for this lattice in practice. And that is a question which is going to be informed by something else I want to talk about. But first, let's talk about how we actually stick these things together. So actual controlled Z gates are hard to make, but there's the so-called fusion operations, which were, the citation is black on blue, I'm sorry, that lets you stick two cluster states together at the cost, maybe it even disappeared. There's supposed to be a citation here, Terry Rudolph, that allows you to sort of glue cluster states together at the cost of some of the photons. So the type 2 fusion gate consumes 2 photons, and where the pre-existing nodes were in the graph, all their neighbors are now attached to each other. So that's where this went away, you now have this structure. And in the fail case, the neighbors talk to each other still, so there's still entanglement between here and there, but the two different clusters are not glued together. And so you can go away and try again here. The issue with the type 1 fusion gate, which only consumes 1 photon, is that in the fail case, you've also broken the cluster. So if you're just sticking the ends together, maybe that's okay. If you actually want non-trivial geometry, you're in a big problem. You have big problems here. And so people think about for larger, to grow up to 1 million qubits, using a lot of type 2 fusion gates. Or in fact, you can show.
Sorry, what's this fusion operation?
It is. Sorry, So I'm going to draw some deeps. You guys want to have tiny chalk. Big chocolate.
I mean, you have two types, right?
Yes. So I take my 2 qubits encoded here, and if I do a Bell state measurement on the 2 qubits, that's type 2 fusion.
Oh, and what's type 1?
Type 1 is you do this, and you do a fancier measurement here. But when you don't get clicks here, what you got put here is a problem. So it's still sort of type 1. The reason that this happens is that in the fail case, you don't actually know what happened. You sort of post-selected on the good event, everything is happy. But if you don't receive the correct heralding pattern, you've now emitted some unknown state into your, I think it's completely mixed state into your system.
So you do Bell measurements,
Yeah.
and I guess that you cannot do better than 50%.
You can
in
if
your
you,
optics.
you can if you use in silico photons. So you can enhance the probability of success of both of these things with if you have a ready source of single photons,
If you have a ready source.
of additional single photons.
Okay. I thought it was a theorem. Didn't know.
So if you have 2 photons that you're doing a Bell state measurement on,
Yeah.
and you have more in silico photons, you can sort of error correct your way out of the problem in some sense.
Okay, that I believe you. But this process itself can, I mean, that's also, you have 50% success.
Yeah.
And then you say if you do a Bell measurement, then I guess you get out two bits,
Yes.
or maybe or not, or maybe 1 bit only because.
As I think about it. So yeah, there's 2 bits here, but the relevant thing is that Bell state measurement is teleporting these entangled links onto these entangled links. And so if I start with 2 4-qubit gates, 2 4-qubit clusters, I come out with a 6-qubit cluster.
But I guess success means that you still have to do some correction on
Yes, but the future corrections are also just measurements.
Sure.
Right. There's a lot of keeping track of what basis you're in down the track.
Can you postpone it?
Yes.
It commutes?
Yeah. All the Pauli corrections commute to which is very convenient. It's as soon as you try to do, it's the same magic state injection problem that arises everywhere else. That eventually you have to deal with that. Now you can do better than just a simple, piece by piece fusion operation. If you use a large array with a bunch of heralds and a bunch of input clusters, you can then output a subset of a lattice where some of the nodes are empty and some of them are full, with some filling ratio. It depends on the loss and some magic in here and the detection pattern you happen to get. It turns out that then you can sort of trace, you can always delete qubits in a cluster state or in a graph state, leaving the neighbors entangled with each other. And so the naive thing to do is then to take this thing that's complicated and try to draw out a simple lattice just by deletions. Now that's expensive in qubits, and maybe we can do better, but this is sort of the obvious thing to do. Now you can just run your normal machinery off of this. And we're good at making unitaries, so this makes me happy. Now, back around to the question earlier, the question of what geometry allows for the most error while still maintaining a large cluster is an open one. But it can be shown that if you start with 5 photon linear cluster states, this isn't a perfect node, isn't perfect success, but you start to see substantial sizes at about 50%. And this is basically is there percolated connectivity throughout the system. Now, it turns out that finding this percolated sublattice efficiently in real time scales badly. And so this is one of those cases where there exists a useful lattice to do your calculation on. But as I understand it, I don't know if it's a scaling problem or just it's sufficiently hard that you can't keep up in real time. But this step of finding a useful sublattice on your cluster state is one that is an open problem. Okay, so here's some open questions. So before I have questions for you, do you have questions for me?
Yes. So the P, the probability of percolating. So what enters in the because you have losses in the fiber, but then you have also like a detector inefficiency, which
same thing. As far as I'm concerned, so to some very close approximation, all losses from failure to generate the photon in the first place to failure to detect it and everything in between are all morally equivalent. And that's pretty close to mathematically true as well.
right, but do they have the same effect? Because if I like,
So in some sense, it commutes. If you do things correctly. If you do things badly, they don't. You can bias in various places, but you can mostly debias everything so that they're. A question that I haven't even started thinking about is if it's useful for them to be biased. But certainly in terms of calculation, it's easier if they're not. So in fact, these clusters that I'm showing here, the assumption is that they're independently degradable. So in the event of loss, any one of them being missing is equally probable, and therefore the loss of any particular one doesn't give you information about the remaining.
But this information, if I understand correctly, this is sort of the left one is the ideal cluster state that you would want to have, but then you have these losses and somehow some of these edges are not there. Depending on the piece, you get the left picture and the right picture.
Yes. So if you lose too many photons, you wind up with patches of connected photons.
But this information that you have there, when do you get that?
So this is the detection rate. So you can calculate sort of this or some approximation of it from the detection pattern here. And then you still have to implement an error correcting code for additional losses from that point forward.
I mean, because you get them somehow slice by slice. Well, you don't get the whole thing and then
So
take your time to examine it and then decide what to do.
So one very good question is, do I have to keep around more slices in order to sort of trace my wires through time as I lose photons? I don't know. I assume that, in fact, the depth direction, the time direction, having more layers will get you a better error. But I believe that that scaling is not known at this time. Okay. So some questions that I would love to know the answers to, and I think are interesting theory questions to think about. One is, what actual lattices are optimal for computation and for being error correctable, and so on. So in some directions, scale free, in other directions, maybe not. Another question is, we have, some module that does something, right? And that'll feed back into the, what the generically optimal design and the practically optimal design are likely to be different, just because we can't make arbitrary things necessarily. This percolation calculation that I've shown scales pretty badly. As I understand it, people have gone behind other, corporate secrecy veils and started thinking about it. But the gossip is that they've gotten stuck. So is there a better idea? And then percolating a sort of semi-arbitrary graph to a lattice and then throwing away a bunch of that lattice to then do gates feels sort of gratuitous. So can we do better? And can we do better on the fly? That seems like even a hard problem. Now, a thing I haven't mentioned yet is that there are so-called algorithm-specific graph states. And for me, looking at the structure of these algorithm-specific graph states seems like it might inform the questions above. Only recently has people sort of seriously looking at these. Maybe there's something interesting there, particularly if we look at the algorithm-specific graph states for error correcting codes. Is that the graph that they generate sort of interesting compared to just foliating a Torah code onto a 1D lattice? I don't know. And then certainly almost all work right now is being done where the algorithm exists, is implemented in the circuit model, and then converted into a cluster state or measurement-based model. And as far as I know, almost no one has thought about algorithms directly on cluster states. I don't know if that's just because it's hard to think about or because there's not any insight there, but I wonder if even just skipping this step for known algorithms will reduce the total number of qubits that I need or whatever. And I do not know. Let me talk briefly about quite recent work. This is by Peter Rohde and some other folks you guys probably know from, and in fact, our second speaker certainly does know. So I don't actually know if he's talking about this or not. But if you take this circuit and you do some what looks like hideous math to me, it's in tables in the paper, you can spit out a really compact graph state that implements this circuit. Now this is much, much smaller than if you did the naive mapping that I showed earlier, where every CNOT gate took something like 12 or 14 qubits off the lattice to do. If we're doing all of this with only five nodes in a graph. And I don't know what the coloring means off the top of my head, I'm sorry. And can we use these algorithm-generated graph states to do something useful? Now, it seems naively that, going back to the question from John, these are not necessarily repeating in time, and therefore seem like they're harder to make, but maybe we can, it's not so much harder that it's not worth doing. Or can we embed this in some time repetitive lattice? And there are some routines where even if we're overall using a cluster state, some lattice, that we need often enough, we should make a specific graph machine for them, magic state injection, for instance. I'm a little bit tight on time. Oh, I'm over time, so I'm going to skip this last section, and you can just skip the movie. I want to talk briefly about, for those of you that have not yet graduated or are looking for somewhere something new to do, what else can you do with a PhD, right? Other than hanging out in academia forever, which I've tried, but only a few of you get to be professors someday. So you can also go off and do industrial research, and in quantum technology right now, there's lots of that. So, have fun. But say you're sick of research, what else can you do? Well, you can, so-called technical sales is actually a job that mostly involves talking to other companies, other people, other smart people, and really understanding what your company does and explaining it. Some sense it's like teaching customers, clients, strategic partners, what the hell is going on in your company. You can manage people. This accidentally happened to me. And there's just like software engineering jobs. This is probably not the house to talk about chip design, but if you've done written physical simulations of processes, the world's looking for lots of chip designers, both in photonics and just in sort of standard semiconductor stuff. Here is a somewhat old picture of our team. I went and found Ward's picture because he's joined the team just recently. He submitted his PhD at UVA in November now, and will soon be defending. So he gets to have doctor on his title on our website too. But he will be, he officially works with QuSoft 4 hours a week. So the hope is
Eighth, actually.
some number of hours a week.
A variable number.
So one, he's inside your cordon for, if you want to talk about stuff and have the IP remain public, we can do that. You can do that. And then if you want to work with us on super secret stuff, that can also be arranged. But anyway, he's the point of contact for QuiX within QuSoft. As I mentioned, I recently got appointed CTO, so I get to have a box on the top row. And I've kicked out Yelmer. He's now chief scientist within the company. Thanks.